Good morning. This is experiential learning of robust design. The experiment conducted a study of wear resistance of different materials by evaluating wear rate and coefficient of friction under various experimental conditions. This experiment is conducted by Harshith Prasad from RV College under the guide Professor Bharati sir. This study investigates the wear resistance of different materials by measuring wear rate and coefficient of friction. In this experiment, the objective is to identify the optimal material and conditions for minimal wear and coefficient of friction. In this experiment, the methodology used is Taguchi L9 orthogonal array and genetic algorithm optimization, which are both robust design concepts, which helps in optimization of various iteration experiments. These are the factors and levels which can be varied, which is load. Load can be varied up to 30 newtons, increments of 10 newton every time. And sliding velocity 1 meter per second, 2 meter per second, and 3 meter per second. And finally, material type steel, aluminium, and brass. The responses to be measured are coefficient of friction and wear rate. This is the experimental procedure. First step is to select the material, such as in this case different materials steel, aluminium, brass for wear testing. Preparing the specimens with uniform dimensions and surface finishes. Second is equipment of setup using wear test machines such as pin on disc tribometer or reciprocating wear testing machine. In this case, we have used pin on disc tribometer, which is available in RV College of Engineering. Now, ensuring the machine is calibrated and set to the required operating conditions is crucial. Next is testing parameters. Set variables such as applied load, sliding speed, and test duration, and record the initial weight and dimensions of the specimen. Now mount the specimen in wear tester and initiate the tests under controlled conditions. Monitor frictional forces and wear track formation during the test. After the test, measure the material loss by weighing the specimens before and after the test. Examine the wear surface using microscopy or profilometry to assess wear mechanisms. Now let's get down to calculations. Here we are calculating wear rate used by this formula, which is weight loss by load into sliding distance and coefficient of friction, which is gained by tangential friction force divided by normal load. This is the experimental data which has been conducted by varying every factor, and 27 experiments have been conducted and the data is recorded here. For every material there are 9 experiments conducted by varying each and every factors. Now let's get down to Taguchi design. L9 orthogonal array is a Taguchi experimental design used for optimizing processes with multiple factors while minimizing the numbers of experiments. It is based on the concept of design of experiments and is particularly useful in wear testing, machining, and material studies. The structure of L9 orthogonal array is 3 factors at 3 levels, which is 3 to the power 3. In this design, we get 9 experiments instead of 27, which reduces the work for the person, and it is easier to optimize experiments with higher iterations, more than 27. This design ensures that all factor level combinations are distributed evenly, reducing the need for full factorial experiments. This is the orthogonal array. This is an example of an orthogonal array. This is the detailed orthogonal array of my experiment. Here, all type of combinations are done and randomized. Now let's get to the Minitab. Here we have designed a Taguchi table using Minitab, and we have imported all the data from Taguchi orthogonal array into the Minitab. And this part of the table of the previously shown completed table is called coded matrix. It is a transformed representation of experimental factors where levels are mapped to standardized numerical values, typically -1, 0, 1 to 1, 0, 1 to 1, or in this case it is 1 to 3, depending on the number of levels. This transformation simplifies analysis and allows for easier application of statistical and optimization techniques. Now there's also uncoded metrics with responses to be measured here. In an uncoded matrix, the design represents the experimental factors with their actual physical values instead of standardized numerical codes. This matrix is directly derived from experimental setup, showing real world settings for each factor. Now this is the finally completed table where signal to ratio is also been calculated by using smaller to better formula. Now we have done Taguchi analysis, wear rate versus material load velocity. Here is the response table for signal to noise ratios, where we used smaller the better concept, and the graph for it for the main effect plots is parallel to it. There is also a response table for means, and the graph for it is respectively on the side. Now let's come to Taguchi analysis of coefficient of friction versus material load and velocity. Here are the two main effect plots for means and for signal to noise ratio, and the response table for the same is given below. All this has been imported from Minitab. And finally, this is the probability plot of wear and coefficient of friction. Both have been shown here. Mean for wear rate is 5.2 into 10 to the power minus 6, and standard deviation is 2.8 into 10 to the power minus 6. P value for the same is 0.127, and for coefficient of friction, mean is 0.1917, and standard deviation is 0.053. P value for the same is 0.231. After the Minitab analysis, we have come to genetic algorithm. A genetic algorithm is an optimization technique inspired by the process of natural selection. It is used to find the optimal solution to complex problems by evolving a population of candidate solutions through selection, crossover, and mutation. Genetic algorithm is widely used in engineering, machine learning, and material science for optimization problems where traditional methods are inefficient. Steps in genetic algorithm. First one is initialization to create population of possible solutions, each representing a set of parameters. Fitness evaluation to calculate a fitness score for each solution based on wear rate and coefficient of friction. Selection. Choose the best performing solutions for experimentation. Crossover. Combine selected solutions to create a better withstanding, stable, and durable material. And then mutation and iteration to repeat the same process again and again to get the optimized solution. How genetic algorithm can be used for wear resistance optimization. The objective of this is to minimize wear rate and coefficient of friction based on material properties and test conditions. Here the input variables are material type, applied load, speed. Next, fitness function. Combination of every variable is tested and the wear results are collected. Then optimization of the same is done to achieve minimal wear and friction. Benefits of genetic algorithm in wear studies. To find optimal material in test conditions without requiring exhaustive testing. Handles complex nonlinear relationships between wear parameters. Adapts and improves results through evolutionary learning over multiple iterations. Now let's get into detailed steps of genetic algorithm. First, we want to define the problem. We want to minimize both wear and coefficient of friction for all the three factors, which is material, load, and velocity. And then we'll calculate fitness, which is wear rate plus coefficient, which needs to be minimized. Next, encoding the decision variables. In this case, it is 1, 2, 3. Next is creating initial population. Each solution is a set of values, which is material, load, and velocity. Now, selection process. Best solutions are selected to pass for the experimental data and results. Lowest fitness values are better in this case. Next is crossover, which is recombination. Then it is mutation, which is random changes to introduce diversity and randomly modify some values. Now let's come into Python code. I've created a Python code for the same, and in this Python code, the data from the L9 orthogonal array has been imported and used to calculate, compute, and analyze all the results responses to give out the optimized results and the optimized material that can be used for wear testing. These are all the code that has been used. So here you can see the L9 data has been implemented and the combinations have been given. The genetic algorithm setup has been done here. This is the final step of the code where all of the combinations are being randomized and mm, mismatched to find the optimized results. And finally, the output given by the code is this, where the optimized material is steel and the optimized load at which it should be loaded is 30 newtons, and the optimum velocity at which the pin should rotate is 2 meters per second, and the optimized wear is 2.78 10 to the power minus 6 grams per newton meter, and then optimized coefficient of friction is 0.133. Thank you.